Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 16, providing trigonometric identities. Classwork opening exercise says, which of these statements is a trigonometric identity? Provide evidence to support your claim. All right, so far we already are told that we have a Pythagorean identity, and we can use that to find others. So if I take the sine squared of theta plus cosine squared theta equals 1, that's the Pythagorean identity, and I subtract, if I subtract cosine, let me just move this over here a little. I'm going to subtract cosine squared theta from both sides. What's going to happen is these cosine squared theta cancel, and I get sine squared theta equals 1 minus cosine squared theta. So statement 1 is just the Pythagorean identity rearranged, so that is a trigonometric identity. Okay, statement number 2, 1 minus cosine theta equals 1 minus cosine theta for theta any real number. All right, well, the function on both sides of this equation are equal, so they're equivalent. So this is an identity as well. Anything equal to itself would be considered an identity because this is true for any value of theta. You plug in cosine of pi over 2, which is 0. 1 minus 0 is 1. Cosine of pi over 2 is 0. 1 minus 0 is 1. 1 equals 1. It's true. It's going to be true for any value of theta. Statement 3. 1 minus cosine theta equals 1 plus cosine theta for theta of any real number. This is not true. And for instance, the cosine of pi over 2 is 0. So 1 minus, I'll just write it, the cosine of pi over 2 equals 1 plus cosine of pi over 2 would become 1 minus 0 equals 1 plus 0, which is 1 equals 1. All right, so it's true for pi over 2. It'd be true for 3 pi over 2 and 5 pi over 2 and so on. So that if I change this, it can't be for any real number theta. Theta, this is only true if theta equals pi over 2 times or plus some constant times pi, where k is an integer. All right. Any other value is not going to be true. For example, cosine of 0 is 1. 1 minus 1 is 0. Cosine of 0 is 1. 1 plus 1 is 2. 0 does not equal 2. So that's why statement 3 is not an identity. Okay. Now it says using statements 1 and 2, let me not scroll so far. Using statements 1 and 2, create a third identity, statement 4, whose left side is sine squared theta over 1 minus cosine theta. Okay, so we simply start this one with the left side being sine squared theta divided by cosine 1 minus cosine of theta. Okay, there's our left side, equals. Okay, so if I look up here, sine squared theta equals 1 minus cosine squared theta. So how about we substitute that in? 1 minus cosine squared theta divided by 1 minus cosine theta. So all I did was substituted in sine squared theta for 1 minus cosine squared theta, because that's statement 1, they're equal, so I substituted it in, and I just kept the 1 minus cosine theta in the denominator. And this is going to equal, well, 1 divided by 1 is 1. A negative divided by a negative is positive. A cosine squared theta divided by a cosine theta is simply cosine of theta. Okay, so we can conclude that sine squared theta over 1 minus cosine theta is equal to 1 plus cosine theta for all theta. Okay, where the functions on both sides are defined, by the way, we do have a restriction on our domain, and that is when the denominator is 0. So 1 minus cosine of theta can't equal 0. So 1 minus 1 is 0. Cosine theta cannot equal 1. And the cosine of theta equals 1 at 0 plus every multiple of 2 pi times some constant. Okay. All right, so it says for which values of theta is the statement valid? So the left side of the equation in statement 4 is not defined when cosine theta equals 1, which I've already stated, which happens when theta is a multiple of 2 pi. The right side of the equation is defined for all theta. Thus, the equation is true wherever both sides are defined, which is for all theta that are not multiples of 2 pi. All right, page 2 says to discuss in pairs what it might mean to prove an identity. What might it take to prove, for example, that the following statement is an identity? So we have sine squared theta over 1 minus cosine theta equals 1 plus cosine theta, where theta cannot equal 2 times pi k for all integers k. Okay, so since this is discussing in pairs, this is something that you should come up with on your own, but here's an example of what it could be. Okay, so students might come up with various suggestions, such as sine squared theta over 1 minus cosine theta equals 1 plus cosine theta, for theta not equal to 2 pi k for all integers k is an identity if sine squared theta over 1 minus cosine theta and 1 plus cosine theta define the same functions, or if they take the same values for the variable theta. The functions on the two sides should have the same domain, but that alone is not enough to make the statement an identity. To prove an identity, you have to use logical steps to show that one side of the equation in the identity can be transformed into the other side of the equation using already established identities such as the Pythagorean identity or the properties of operation, commutative, associative, and distributive properties. It is not correct to start with what you want to prove and work on both sides of the equation at the same time, as the following exercise shows. Okay, so exercise 1 says, use a calculator to graph the function f of x equals sine x plus cosine of x and g of x equals negative the square root of 1 plus 2 sine x cosine x to determine whether they're equal for all theta, for which functions are defined is a valid identity. You should see the graphs that are functions. You should see from the graphs that the functions are not equivalent. So I'm going to bring that in here. I graphed it in GeoGebra. And so here is the graph. So the green one is right here. And it is true from this point right here down to this point right here, but then it gets flipped. So the reason this occurs is because we cannot get a negative value under a radical, or it's not real. The square root of a negative is imaginary. So if it has to be positive under the radical and then you negate it, then you're only getting negative values. So this is the blue function that keeps going up to 0, but then turning and staying negative. Whereas, so it's a reflection. So wherever this function's negative, it's a reflection, or I should say wherever the sine function's positive, it's a reflection across the x-axis of the square root function. But wherever the sine function, the sine plus cosine function is negative, it's equal. So it's only equal on half of the domain. Okay, so that's what the graphs look like. So it says, suppose that Charles did not think to graph the equations to see if the given statement was a valid identity. So he set about proving the identity using algebra and a previous identity. His argument is shown below. So first, number one, he says, the sine of theta plus cosine theta equals that negative square root function for theta being any real number. Now using the multiplication property of equality, he squared both sides. So that would give you sine squared theta plus 2 sine theta cosine theta plus cosine squared theta on the left, and what's under the radical on the right. Okay. Using the subtraction property of equality, subtract 2 sine theta cosine theta from each side, which would give, so what are they saying here? Let's follow along. Using subtraction of property of equality, subtract 2 sine theta cosine theta from both sides. So he subtracted this from both sides. So that would cancel that. And it would go away here. And you get sine squared theta plus cosine squared theta equals 1, which they have here for theta being any real number. Statement 3 is the Pythagorean identity. So replace sine squared theta plus cosine squared theta by 1 to get 1 equals 1, which is definitely true. Therefore, the original statement must be true. Okay, so does this mean that Charles has proven that the statement 1 is an identity? Discuss with your group whether it is a valid proof. If you decide it is not a valid proof, then discuss with your group how and where his argument went wrong. Okay, so here's the argument. No, statement 1 is not an identity. In fact, it is not true, as we showed above by graphing the functions on the two sides of the equation. The sequence of statements is not a proof because it starts with a false statement in statement 1. So you can't start a proof with something that's not true. Squaring both sides of the equation is an irreversible step that alters the solutions to the equation. When squaring both sides of an equation, we have assumed that the equality exists, and that amounts to assuming what one is trying to prove. A better approach to prove an identity is valid would be to take one side of the equation in the proposed identity and work on it until one gets the other side. Okay, so you'd start with sine theta plus cosine theta and try to turn that into the negative square root 1 plus 2 sine theta cosine theta. But in this case, it would not be possible because it's not true. Okay, page 3 brings us to example 1, 2 proofs of our new identity. Work through these two different ways to approach proving the identity sine squared theta divided by 1 minus cosine theta equals 1 plus cosine theta, which we did on page 1, where theta does not equal multiples of 2k pi for integers k. The proofs make use of some of the following properties of equality and real numbers. Here, A, B, and C stand for arbitrary real numbers. So this table here is just a review of what you should already know coming into Algebra 2, reflexive, symmetric, transitive properties, properties of equality being addition, subtraction, multiplication, and division, and substitution, associative, commutative, and the distributive property. All those properties should be known. All right, fill in the missing parts of the proofs outlined in the tables below, then write the proof of the resulting identity. We start with the Pythagorean identity. When we divided both sides by the same expression, 1 minus cosine theta, we introduced potential division by 0 when cosine theta equals 1. This will change the set of values of theta for which the identity is valid. So here's a proof. So step 1, the left side of the equation is sine squared theta plus cosine squared theta equals the equivalent right side, 1. Domain is theta for any real number. That's the Pythagorean identity. It works for everything. Step 2, we ended up with sine squared theta because we subtracted cosine squared theta over to the other side. Domain, still theta, any real numbers. What property was that? Well, it's a subtraction property of equality. Okay, so then the next step is, this is blank, so we need to fill that in. Okay, so nothing changed on the left. So we're just going to write the sine squared theta equals, and this is 1 minus cosine theta times 1 plus cosine theta, for theta being any real number. Okay, so that's a, oops. Okay, so that's a distributive property. So if I were to distribute this now, 1 times 1 is 1. 1 times cosine theta minus 1 times cosine theta cancels, and a negative times a positive is negative, and cosine theta times cosine theta is cosine squared theta. So that's the distributive property in reverse, if you will. And then number 4, step 4, here is where we divided both sides by 1 minus cosine theta. So this is going to be sine squared theta divided by 1 minus cosine of theta. So what they did here on the right, they divided this by 1 minus cosine theta. So what you do to one side, you must do to the other, and that is the division property of equality. Okay, the domain changed here. Now we have a restriction on theta. Theta cannot, or 1 minus cosine theta cannot equal 0. So cosine theta cannot equal 1. So cosine theta cannot be pi over 2 times multiples of. So let me bring that in. Shrink it down so it fits in here. Okay, so it's theta cannot equal 2 times pi k for all integers k. All right, so for now we have sine squared theta over 1 minus cosine theta. And what happens here is the 1 minus cosine thetas cancel, and we're left with 1 plus cosine theta on the right. Okay, and then the domain doesn't change. And the reason is substitution property of equality using 1 minus cosine theta over itself is equal to 1. So that right there. In other words, it cancels. It's a bad thing to say, cancels out, because it doesn't just disappear. It equals 1, and then 1 times 1 plus cosine theta is 1 plus cosine theta. That is actually the multiplicative identity when you divide something by itself. Okay, page 4 brings us to the second way to do this. So part B says, or we can start with the more complicated side of the identity we want to prove and use algebra and prior trigonometric definitions and identities to transform it into the other side. In this case, the more complicated expression is sine squared theta divided by 1 minus cosine theta. So we take sine squared theta divided by 1 minus cosine theta equals 1 minus cosine squared theta over 1 minus cosine theta. So what happened there was the substitution property of equality using sine squared theta equals 1 minus cosine squared theta. So we did this already on page 1. All they did was took this and put this in its place because we have an identity that says they're equal. It's just an adjustment of the Pythagorean identity. So step 2, this isn't going to change. The right side changed. So this is still going to be sine squared theta divided by 1 minus cosine of theta. What happened here was 1 minus cosine squared theta became 1 minus cosine theta times itself divided by 1 minus cosine theta. That is the distributive property. The only thing we need to fill in here is the domain. The denominator is still 1 minus cos theta, 1 minus cos theta on both sides. So it's still going to just be theta does not equal 2 pi k for all integers k. So that's still the same. Part 3 says sine squared theta over 1 minus cosine theta equals 1 plus cosine theta. So what happened here was, okay, we often in math just say these cancel, but what actually happens is 1 minus cos theta over 1 minus cos theta is 1. Anything divided by itself is 1. And 1 times 1 plus cos theta is 1 plus cos theta. And that's a substitution property of equality. Okay, so substitution property of equality using 1 minus cos theta over 1 minus cosine theta equals 1. And yet again, our denominator did not change. So this is going to equal the same thing. Theta cannot equal 2 pi k for all integers k. Okay, exercises 2-3. Prove that the following are trigonometric identities. Beginning with the side of the equation that seems to be more complicated and starting the proof by restricting x to values where the identity is valid. Make sure that the complete identity statement is included at the end of the proof. Okay, so the first thing we're going to do is say that we're going to let x be a real number so that x cannot equal pi over 2 plus pi times k for all integers k. All right, because we have, and we're going to start with the more difficult side. So we're going to start with what appears to be more difficult is the right side. Okay, tan x is just tan x, and we have secant x divided by cosecant x. So we're going to start with that on the left. Okay, and then what is secant x? Well, remember, the way to remember these, because a lot of students confuse the inverse of sine and cosine, which is which. SEC, cosine backwards is COS. The only difference is that. So this is the inverse of cosine. So I'll rewrite that as 1 over the cosine of x divided by 1 over the sine of x. Okay? So remember, when dividing a fraction by a fraction, you multiply by its reciprocals. So then you would say the secant of x over cosecant of x equals 1 over cosine x times the reciprocal of the denominator, sine of x over 1. So then we say the secant of x over cosecant, cosecant x equals, notice the left side never changes, sine of x times 1, cosine of x times 1 will give us sine of x over the cosine of x. And then finally, we would say the secant of x divided by the cosecant of x equals, well, sine x divided by cosine x is tan x. Okay, so therefore, secant x over cosecant x equals the tangent of x, where x cannot equal pi over 2 plus pi times k. All right, page 5, number 3 says the cotangent of x plus the tangent of x equals secant x times cosecant x for all real numbers x that cannot equal pi over 2 or do not equal pi over 2 times some n. Okay, they could have used k here for consistency, but n is okay. All right, so if we're going to start by using the more difficult side to be on the left, and you look at this and you're like, they're both looking pretty difficult. Well, the next thing you need to do is, this is one term. This is two terms. A plus sign separates terms. So two terms is more complex than one term. So the first thing you're going to do is you're going to say, let x be any real number so that x does not equal multiples of pi over 2 times k for all integers k. Then we would express cotangent of x plus tangent of x in terms of sine x and cosine x and find a common denominator. Okay, so that's what we're going to do. We're going to start with cotangent x plus tan x on the left. So I'd write cotangent x plus tangent of x equals. So we're trying to get to this. So cotangent x is the inverse of tangent, and tangent is sine over cosine. So cotangent is cosine of x divided by sine of x plus tangent, which is sine of x over cosine of x. So that's the first thing we do. We take cotangent x plus tan x and we rewrite it in terms of sine and cosine. Okay. So now I need common denominators if I'm going to add fractions. So if I have sine x, cosine x, and sine x, cosine x, like so, I need a sine x times a cosine x in the denominator. So I'm going to multiply this piece by sine x, or I'm sorry, just cosine x. I need a cosine over here to get sine x cos x. So I'm going to multiply by cosine x over cosine x. And I'm going to multiply this by sine of x over itself. Okay, so this is equal to 1, this is equal to 1. I didn't change the values of this. And over on the left, I'm going to get, oops, what did I hit? Undo. I'm going to get sine x times cosine of x. For my denominator, and the numerator is going to be cosine of x times cosine of x, which is cosine squared x, plus sine x times sine x is sine squared x over that same sine x times cosine x. So now I have common denominators, and actually I should have an equal sign here and an equal sign here and an equal sign here. So then I get cosine squared x plus sine squared x over sine x times cosine of x. All right. So this is the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. And I get sine x cosine, 1 over sine x times cosine of x. All right, so now we're coming together here. If I separate this now, this is the equivalent to 1 over the sine of x times 1 over the cosine of x. And 1 over sine x is cosecant. And 1 over cosine x is secant. Whoops, why am I writing 1 over? 1 over sine x is cosecant x. 1 over cosine x is secant x. So we get cotangent x plus tan x equals cosecant x times secant x. And that's what we have here. They're in opposite order, but multiplication is commutative. And therefore, cosine x plus tan x does equal this for all real numbers x, such that pi over 2 times n, such that x does not equal multiples of pi over 2. Okay, page 6 brings us to the end of lesson 16. Go to your problem set.